Welcome to video 5 for this unit on Pythagorean theorem and irrational numbers. In this video, we're going to focus on cube roots and decimal representations. We learned earlier that the side length of the square is the square root of its area. In this diagram, the square has an area of 16 square units and a side length of 4 units. These equations are both true. 4 squared equals 16, and the square root of 16 equals 4. Now think about a solid cube. The cube has a volume, and the edge length of the cube is called the cube root of its volume. In this diagram, the cube has a volume of 64 cubic units and an edge length of 4 units. These equations are both true. 4 cubed is 64, and the cube root of 64 is 4. We say that the cube root of a number n is the number whose cube is n. It is also the edge length of a cube with the volume of n. Here are some other values of cube roots. The cube root of 8 equals 2 because 2 cubed equals 8. The cube root of 27 equals 3 because 3 cubed equals 27. The cube root of 125 equals 5 because 5 cubed equals 125. We can approximate the values of cube roots by observing the whole numbers around it and remembering the relationship between cube roots and cubes. For example, the cube root of 20 is between 2 and 3, since 2 cubed equals 8 and 3 cubed equals 27, and 20 is between 8 and 27. Similarly, since 100 is between 4 cubed and 5 cubed, we know the cube root of 100 is between 4 and 5. Many calculators have a cube root function, which can be used to approximate the value of a cube root more precisely. Using our numbers from before, a calculator will show that the cube root of 20 is approximately 2.7144, and that the cube root of 100 is approximately 4.6416. Let's plot one more number, the opposite of the cube root of 1/8. A complicated-looking numerical expression like this can be a rational number. We saw earlier that 2 cubed equals 8, so 1/2 cubed equals 1/8. This means that the opposite of the cube root of 1/8 is a rational number because it equals -1/2. But every number, rational or irrational, has a decimal expansion. Sometimes the expansion goes on forever. For example, the rational number 2/11 has the decimal expansion 0.181818 repeating, which means that the 1 and 8 pattern repeats forever and is written as a line over the numbers that repeat. Every rational number has a decimal expansion that either stops at some point, like the opposite of the cube root of 1/8, which is -0.5, or ends up in a repeating pattern like 2/11. Every irrational number has an infinite decimal expansion that does not stop and does not end up in a repeating pattern. From the decimal point of view, we can see that rational numbers are pretty special. Most numbers are irrational, even though the numbers we use on a daily basis are more frequently rational. Thank you for watching video 5 of 5 for this unit on Pythagorean theorem and irrational numbers.